Yeah. See, check your screen is visible.
Yes,
Please.
sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, 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 ma'am, okay. So, what about here? Only 37, 36. So, wait at least 1 or 2 minutes, then I will start. Okay, so 120. Okay, shall I start? Yes.
Yes, sir.
Okay, okay, ma'am. Okay. I think they are coming one by one. See, 5 minutes, only 40, 41 is there, yeah, out of 671. But anyway, okay, see, listen. So today go to take the some two lectures more. Okay, that eighth one is most probably already you know. Okay, that is IV characterization of PN junction diode. Based on that, you go to see the next ninth one. Okay, the when that eighth one I go to explain little bit, but the ninth I go to explain in detail. Okay, that lecture number 9. That IV characterization already you know. Okay, screen is visible for you. Please confirm.
Yes, sir. It's visible.
Okay, see, the lower classes you studied the IV characterization and module 2 also already have the same is repeated here. Okay, but anyway, the little bit I'll go to explain because the next one is ninth one. It will be helpful for you. See, once the PN junction is formed, what happened immediately? The diffusion takes place. Is it correct? Say yes or no. See,
Yes,
once
sir.
once the junction is formed, so automatically the diffusion, the majority charge carriers from N region and the majority charge carrier simply cross, okay, diffuses each other. So due to this, that N side, for example, the N region, the positive voltages are there. Similarly, in the P region, the negative electrons is available. Okay, so in between, a strong potential barrier is created. In between, the very strong potential barrier. So this potential barrier restrict the majority charge carriers flow away from the junction. Okay, so that's why you say that potential barrier is very important here. For silicon and germanium, what much amount of that potential barrier is there? See here, the diffusion layer for this silicon is up to zero point 0.7 volt, and germanium that is up to 0.3 volt, 0.3 to 0.35. Okay, roughly 0.3. So this potential barrier is always exist even the device is not connected to any other external circuits, external sources. Okay, are you understand this point? Say yes or no.
Yes, sir.
Yes. Okay, now so this barrier, so this potential barrier where is formed in between the two junctions, okay, that PN junctions, and this I think this already you know. Now what happens when the diode is connected to forward bias and reverse bias like that the case is already discussed. Okay, that characterization also already you did, that experiment also already you did for both the forward bias and reverse bias characterization. The curve is also drawn. Okay, when the diode is connected to forward bias, what happens? What is the meaning of forward bias? that P is connected to positive and N is connected to negative. Okay, then positive to positive, negative to negative, you say that is a forward bias. So due to this, and the width of the region goes on decreasing. There is no doubt because the like charges repulse each other, so they go to push the depletion region on both sides. The region goes on decreasing when the applied input voltage exceeds the potential barrier. For example, silicon that is 0.7 volt or 0.3 volt exceeds, simply there is no potential barrier. So that time the charge carriers, majority charge carriers, are very easy to cross the junctions. Very easy to cross the junctions. See here, so they require to cross the junction as width of the depletion region around the PN junction is decreased. When the same PN junction is connected to reverse bias, what happens? That is like charges. Okay, attraction is there. So there's no doubt that is pulled by the external source. The depletion region, width of the region goes on increasing. Width of the region goes on increasing. Okay, so due to this, the diode does not conduct. You say that is off state like that. The width of the region goes on increasing. So this happens, the diode is connected to forward and reverse bias conditions. Okay, when what is the characterizations here? So when the circuit is connected, see the diagram is visible for you. Please confirm.
Yes, sir.
Yes, sir.
Yes. See that N is connected to negative and P is connected to positive. You see that is forward bias, and applied input voltage exceeds this 0.7. For example, silicon or 0.3 for germanium. So definitely the potential barrier opposition will be overcome and current will start to flow. So that is given in the diagram. See here, when both the forward applied forward bias voltage increases, see initially there is no current. Okay, simply there is no current starting from zero, and the current slowly increases at one stage where the applied input voltage reaches the barrier potential. For example, 0.7 for silicon or 0.3 volt for germanium. So that time, okay, suddenly the depletion region vanish. So the current increases enormously. See here, the next there is a small variation in the voltage. So suddenly the current will increase like this. See here, the current will increase, immediately increase. Up to that, see simply the slowly increase the current. So after the applied input voltage exceeds the potential barrier, so your current, forward current increases. So due to this, the enormous amount of current also increases where the input voltage reaches some point. You say that is a knee point here. That is a knee voltage. I think you studied in the lower classes. Is it correct? Say yes or no?
Yes, sir.
Yes, sir.
Yeah. So this knee point, why you say in the characterization curve, the current goes on increasing here, but one stage where the voltage reaches the knee on the static curve, the high current flow through the diode, and there is a small variation in the voltage with a little increases in the external voltage. So this point where the sudden increase the current takes place is represented on the IV characterization is called knee point here. That is called knee point. The corresponding voltage you say knee voltage. So what happens due to this? So the sudden increase of current also some causes damage in the devices. So that is the reason, and the diode always connected in series with some resistance here, resistors. The reason is the resistors control the flow of current. See here, therefore the resistors are used in series with the diode to limit the current flow, because it exceeds certain value, it definitely go to causes the damage. So that reason, see here, that causes the device to dissipate more power in the form of heat. What happens? So when the heat is produced, automatically the device goes to damage. So that is the reason some the circuits, for example, most of the where they were using the diodes, these resistors are connected in series or something. And same happened in the reverse bias also. But in the reverse bias, again that some breakdown voltage is coming. See here in the next, you go to see the reverse bias. So see the region. What is the width of the region here? The reverse bias, N is connected to positive and P is connected to negative. Say the width of the region goes on increasing here. So this results the depletion region grow wider due to the lack of electrons and holes presence and due to very high impedance and almost in the insulator. Okay. Now what happens? Some small amount of current also flow in the reverse bias condition. That is in terms of microamperes. Okay, see here in the diagram, a small amount of current. When the voltage increases, the reverse voltage increases, and the current remains constant. See here, almost the current remains constant at one stage where that reverse voltage reaches certain point. You say that is a breakdown voltage. So at that time, the current increases suddenly, the reverse saturation current increases, so it will causes the damage for your diode. So how you go to avoid such condition? Okay, you carefully handle the reverse bias. So that's why they go to take some special devices similar to your forward bias. The reverse bias also the diode will conduct. So such diodes are called, what is the name? What is the name of such diodes? You studied in the lower classes. Yeah, please, anyone? What is the name? Yeah. Yeah, I think you studied. See, in the characterization curve, the forward bias, you say the diode will conduct like that. But reverse bias, simply the depletion region increases, there is no conduction.
Zener.
That is Zener diode. Yes, the Zener diode is a voltage regulator. So why you go to take the reverse bias also diode will conduct. See here, a small leakage. So here, however, a small leakage current will flow through the junction as measured in the microamperes. Again, the reverse voltage increases. Okay, sufficiently is enough. It will causes the diode to overheat and fail due to the avalanche effect around the junction. And this causes due to the diode become shorted and will result in the flow of maximum current in that circuit. You step down the diodes. So you say that is a breakdown voltage or reverse breakdown voltage. Okay, so this particular voltage you say reverse breakdown voltage. So diode breakdowns occurs by two mechanisms. One is avalanche, other one is Zener breakdown. So the Zener diode is especially making diode. So it will conduct both forward as well as the reverse bias. So that is the reason the diode is acting as a voltage regulator. I think you studied in the lower classes. Yes. So why the Zener diode is acting as a voltage regulator like that? Are you remember?
Yes, sir.
Yes. So this happens. Okay, that forward and reverse bias happens. So please here you clearly understand when the diode is connected to forward bias, where width of the region decreases. At the same time, when the diode is connected to reverse bias, the width of the region increases. Both the cases, the width of the region either increasing and decreasing. What happens? The potential barrier, the potential barrier region goes on increasing and decreasing like that. So basically, what happens? That is our next lecture number 9 is DLTS. So before you move on to that, I will say some few points, something that. Okay, so how you go to take that PN junction diode from the pure germanium and silicon? See, for example, how you go to make P type semiconductor and type semiconductor? Ma? By, see, there's a pure semiconductor is there, germanium or silicon. So I want to take P type semiconductor. What can I do? Simply that the pure germanium or cluster doped with certain impurities, that is a trivalent impurities, or n type means again that is doped with pentavalent impurities. Is it correct or not?
Yes, sir.
Yes,
Yes.
sir.
Okay, when the impurity is added to the pure crystal, okay, so definitely the crystals and the pure crystal is ideal one, or the crystals having certain defects.
Certain difference.
Definitely the defects are there, there's no doubt, definitely some defects is there when the doping takes place. So when the pure germanium or silicon are doped with certain impurities, so there's no doubt that the defects they may be filled by these impurity atoms. Is it correct?
Yes, sir.
Yes. So the different type of defects I think you studied. Okay. Anyway, I any doubts here more in this lecture 8? I think that is
No, sir.
already no. Okay, that's why I go to stop. This is normal P that VA characterization. So now I go to share this one more slide, that lecture number 9. Okay, that is a continuation because the PN junction diode very easy to understand now. Just wait. Okay, so now you please just wait. I go to take this one. Yeah, screen is visible, please.
Yes, sir.
It's visible now. Okay. So this is a DLTS. DL, that is a deep level transient spectroscopy. Okay. So that is a technique. It's nothing but a technique to measure the transient spectral changes, the capacitancy. That's all. I go to explain. No problem. Okay. Now, based on this, you see so many defects are there here in the normal crystals. The so many defects. What are the defects here? Is vacancies. I think you know. Maybe sometimes the atoms are displaced in that void space. You say maybe they go to give some void space. You say that is vacancy here. That's missing of atoms. So once such crystal is doped with certain impurities, so the substitution impurity is added. See, the extra impurity atom is come to occupy the original region. See here. So here that vacancy is there. So in that vacancy, maybe the impurity atom they go to occupy such vacancies here. So that is a substitution, or the self interstitial or interstitial impurity atoms. Maybe some other one go to occupy that position. See here. So basically in this position there's no atoms, but see here someone they go to occupy this space. So that is a self interstitial. So these type of defects I think already is there in the crystals. Such crystals are doped with materials, that impurity materials. This doping material they go to occupy certain positions. So this vacancies he goes to the trapping, traps. Traps means maybe that vacancies are available or something. Okay, when the forward bias and reverse bias condition, the width of the region either increasing and decreasing. So due to this, the trapping level is filled sometimes, and the charge carriers from the trapping level is coming out of, and that is emission of the charge carriers from that trapped level. This emission of charge carriers from the trapping only you go to measure with the help of this spectroscopic technique, DLTS technique. Okay, so these defects are the already you know. Now you come to the what is the basic principles of DLTS. Basic principles of DLTS. See, and the first is the emission of trapped charge carriers. Please carefully listen here. The emission of trapped charge carriers, where in the depletion region. Okay, the depletion region carriers change the depletion capacitance C of MPN junction or any other metal semiconductor junction that Schottky diodes are. For this, the transient measurements gives the information of the defect level in that crystal or in that band gap. Can you understand this? Say yes or no, please.
Yes, sir. Yes,
So
sir.
the emission of trapped charge carriers change the depletion capacitance C, okay, of PN junctions. So this measurements gives the information about what much amount of defect level is exist in that band gap. So how that variation takes place, that depends upon the applied input voltage. There is no doubt. See, the deep level, the transient spectroscopy is nothing but a method to measuring or the determination of the concentration as well as the thermal emission rate of semiconductors in deep levels by measuring the capacitance transient as a function of temperature with respect to temperature also. So normal p-n junction diodes or Schottky diodes, you know what happens when the diode is connected to forward bias as well as reverse bias. In both the cases, how the traps they goes to fill when the charge carriers are coming out of the trapping levels. Now I go to explain one by one. When the diode is connected to forward bias, what happens? The width of the region goes on decreasing. Okay, so that is filling of traps. When the diode is connected to reverse bias, so simply that is the emission of charge carriers from the trapping levels. So that is given here. See, the forward bias is to fill the traps, then the capacity transient caused by the carrier emission from the filled traps when the diode is connected in the reverse bias. Can you understand this concept clearly? Please.
Yes, sir.
See, definitely the defects are there, there is no doubt. So how the trapping levels are filled? By using the forward bias. when the charge carriers is coming out of the trapped levels at the reverse bias. So due to this, so how the forward and reverse bias takes place? Simply you go to vary the input voltage. See, applied input voltage changes automatically. The width of the region also changes. What is the reason? Already I told. So just now I told. For example, I go to maintain that input applied input voltage in between 0 to 7 or 0 to 3. There is no doubt the width of the region increase and decrease like that. So if beyond 0.7, maybe the depletion region is vanished, or beyond 0.3 for germanium, it is okay. But I go to maintain in between that, so increase, decrease, increasing. So this increasing, decreasing changes the capacitance, transience capacity in that region, depletion region. So that depends upon the voltage. You go to see here. So the next point. So how it goes to change when the voltage across the PN junction is changed, and there is corresponding changes in the depletion region width. So this changes in the width causes the changes in the number of charge carriers on both sides of the junction, resulting in the changes in the capacitance. Are you understand this? You understand or not, please?
Yes, sir. Yes, sir.
Yes. As due to thermal, for example, whether I go to increase or decrease the temperature, see a thermal emission rate of the trap is same that of the rate window. Sometimes the strong temperature dependence of the trap emission rate provides to resolving the emission from the different trapping levels. So if you go to increase, due to the thermal agitation also, maybe the charge carriers is coming out of the trapping levels. So there are two different ways you go to take that content. One is forward bias. You say that is a junction capacitance. The other one is a diffusion process. You say that is a diffusion. See, the contribution due to changes in the depletion width. You say that is a junction capacitance. And the contribution due to the change in minority charge carriers, that is called diffusion. So diffusion means uh, inside the charge carriers will flow. So when the charge carriers will flow here and there, if there is no junction depletion region, simply the charge carriers will flow. So that is due to diffusion capacitance. There are two different cases is there. So how that increasing decreasing takes place? Okay. So how the capacitance? The general formula I think you know. The capacitance of capacitor is given by that C is equal to epsilon naught A by D. Is it correct?
Yes, sir.
Yes, sir.
So what about D there? I think you studied D is the distance between the two plates like that. So here D is replaced by W, that is width of the depletion region. So with respect to the W, your capacitance increase or decrease. How? That depends upon the W value. See, the changes in width causes the changes in the number of free charge carriers. Due to this, there is a change in the capacitance. So now I go to show the diagram here. Okay, please understand. So this is the normal P and this is a normal N-type semiconductor, and this is the PN junction. So this width W is there, that is the width of the potential barrier. So the capacitance is given by this equation. C is equal to epsilon naught A or epsilon A by D. So instead of D, the W is there now. So the connections, this is a normal P and this is an N-type. What happens when the junction is formed? So when the PN junction is formed, so how this energy level changes? See here, this is a normal case. EF is very close to EV. For N-type, EF is very close to EC. So when both are joined, so this is your EF level now. This is your EF level. So this built-in potential created here. See, the built-in potential created here. In between, and the difference is given. Okay. In a class, see that the Q V naught is there. Okay. Q, that is a built-in potential generated here. See, this is a built-in potential. So, that the connections of P and N-type region, these are normal cases. And how the variation takes place, you go to see the next diagram. See here, the equilibrium condition. So this is the normal built-in potential. When the same is connected to forward bias, the width of the depletion decreases. See at the same time, see here, the potential, your built-in potential also decreases. When that is connected to reverse bias, see your region goes on, that the built-in potential goes on increasing. That depends upon Q into V0 plus VR. This is V0 minus VF like that. This is normal case. This is a normal case. That depends upon the doping concentration, whether it is high level doping or low level doping like that. When the doping is high, the W is too small. When the doping is low, definitely W is more. Okay, so that is given in the, you go to understand the diagram. Yes, say yes or no. See whether you understand the diagrams or not, please.
Sir, what is F?
Which one? That is Fermi energy. Yeah, Fermi voltage at Fermi.
Oh, yes, sir. Yes.
Fermi energy. The width of the region is given. W is given, sir, there. Okay. Applied voltage is there. Yeah, forward voltage. That V suffix S. Forward voltage is given. Is it correct? Say reverse forward. VR means reverse voltage. VF forward voltage. Forward bias and reverse bias voltage. I understand. Say yes or no, please.
Yes, sir.
The VF, yeah, that forward voltage and reverse voltage is mentioned there. VF, VR. You see the diagram. The dotted lines indicates the Fermi energy. That is Fermi level. Yes. See whether you understand this diagram.
Yes, sir.
Yes. Okay. Now come to the next point here. See, once when the junction capacitance is dominant under the reverse bias. So under the reverse bias, the width of the region goes on increasing. Okay. That time the junction capacitance takes place. So because that is depends on the width. When the diode is connected to forward bias, diffusion process takes place because the width of the region decreases. The majority charge carriers diffuses each other in the where in the junction region. So the diffusion capacitance is dominant under forward bias conditions. Are you understand? Say yes or no. So when the forward bias, when reverse bias happen, why junction capacitance? Why you say that is a diffusion capacitance? Are you understand or not? Please say yes or no. I think it's not there. Okay. See next. See, can you hear me or not here? There's no response from that side.
Yes, sir.
Yes, sir.
Yes. Then when the same PN junction, whether you go to the deep level, for example, you go to take that one, according to that Shockley and Hedal, and they go to give some expressions here. So that is, and the product of the whole emission rate and the filled rate. So that is a density of the filled state, the traps, is equal to that EP plus En of NT. So here the capital NT is nothing but the total density of that deep states. Small nt is the density of the filled traps density. So what much amount of that states are filled where in the trap level. The n capital T, the capital NT is nothing but the total density. So the product of EP NT is equal to, again that is a product of the sum of En and EP into NT. So that is a equation is given by Shockley and Hedal. So based on that, you already explained these diagrams. So what when the PN junction is formed? So what about your width of the region? Again, you come to the forward bias and reverse bias. What happens? So how the defects are filled? So these type of defects already is there. How these they go to fill? The next diagram. So how you go to take that electron and hole emission trapping takes place. So that is the next diagram. See in the deepest level. So for example, in the normal region that in between the valence band and conduction band, that is in the energy gap, please understand, when both Cn and Cp are equal, okay, maybe you go to say that is a recombination center. See here exactly at the center. So this is Cp and this is Cn more, the capacitance of the N and P regions. So both are almost equal. You say that is a recombination. So when Cn is greater than Cp or Cn is less than Cp, you see the electron trapping or hole trapping. So when Cn is far greater than Cp, so that is electron trappings. In that case, they mostly interact with the conduction band. When and the Cp is far greater than Cn, so that is a hole. Maybe mostly they will go to interact with the valence band. So this is the corresponding diagram. So where Cp, Cn are equal, that is recombination. When the Cn is greater, electron trapping. Cp is greater, that is hole trapping. And the corresponding emission rate is also there. En and Ep is there. So just now you see the formula. En, electron emission, okay, hole emission like that. So this is the concentrations of electron and the hole emission rates here. So based on that, you go to identify which one, the defect level in that band gap. So what are the defect levels in that band gap? So you go to measure both voltage as well as the capacitance, and you go to draw the corresponding graph with respect to time. See here, with respect to time, I do go to draw the graph here. Okay, please, 1 second. Hello, sir. Hello, madam, ನಾನು ಕ್ಲಾಸ್ எடுத்துட்டு madam, 1 second, please. நான் இந்த முடிச்சிட்டு வரேன். Okay, madam. Okay, see, the diode kept at fixed reverse bias. Okay, so now you go to measure the voltage here. So this is with respect to time, how the variation takes place. Okay, the reverse voltage remains constant and increases again constant like that. At the same time, so how the capacitance goes to vary like this. See here. So this is in the reverse bias condition. The capacitance at the reverse bias condition, the C of t is equal to C of Rb minus delta C naught exponential of minus ENT. So that is exponentially increasing term. See here, exponential increases here. Okay. Okay, please understand. So this process is identified once again. The one more diagram you see here. See, in the A, please understand, this is a conduction band and valence band. Please understand that is EF level more. So this here, the dots are there. What about the dot indicates that is empty defect states. Now, these empty states are filled when the diode is connected to forward bias. See here, B, when that is connected to forward bias, the width of the region decreases. See here, W is decreases, and almost all the defect levels are completely filled. When C, again, the diode is connected to reverse bias, the width of the region increases. But at the same time, not all the trapping levels are coming out. Slowly will come. When, so that is a C. Come to D, emission case. When the deepest level in the reverse bias condition, again you go to see some of the atoms from the defect level coming out. See here, the width of the region is same. Maybe see here is fully completed. Here some of the atoms is coming out. So deepest level, where in the deepest level, so this atom coming out in the diagram, we go to see here, coming out of this one, the defect filled state and the empty state. So the filled states are completely, each and every trapping is emission of the charge carriers. Emission of charge carriers. So that is given in the A, B, C, D region here. That is A remains constant, increasing. So that is a small, again is connected to reverse bias, is decreasing and is slowly increasing like this. Can you understand? Yes.
Sir, can you explain C diagram? That's C.
C means reverse. See, B is forward bias. That entire defect level is completely filled. See here. When the connected is reverse bias now, width of the region increases. Okay. So after that, what happens? Slowly the trapping level and that emission of trapping starts. So at the same time, see here, the defect level increases here. So this defect level, the atoms are coming out where from that filled state. So these are the filled state. So now the concentration goes on decreasing because each and everyone is coming out of that surface. So that is happened in the reverse bias condition. That is happens in the reverse bias. See, this is a normal case, equilibrium condition. This is forward bias. So these are the reverse bias condition. So return to the reverse bias with change in the capacitance and the emission occurs. That is emission occurs. Again, all are emitted. For example, each and everyone is emitted. Now these all the filled states are completely empty. So now they come to the equilibrium position like this. Okay, and you understand?
Yes, sir.
See, equilibrium condition, forward bias, reverse bias, and slowly comes to where? Again that equilibrium condition. So this is one cycle. This is one cycle. Okay.
Okay, sir.
Yes, anything else here? Your doubts? Any doubts or anything else, please? Then with respect to temperature, see, with respect to temperature, the timing, now the capacitance timing with different time intervals. I think this graph is not necessary, but anyway, they will give certain things here. So each and every time, so the normal cases, what about the concentration increases, the temperature? So this is at room temperature, temperature goes on increasing. Okay, see here, how they go to variate with respect to temperature here in this curve. This is a capacitance transient. You remember this equation that delta C naught is equal to NT, already told, by 2 ND into CRB. That ND is nothing but a donor concentration. Okay, carrier density or ND, and CRB is a capacitance in the reverse bias condition. That small NT, capital NT already you discussed. That ENT already you know. Okay. Anything else, CMO? Any doubts or anything? Please. Any doubts?
No, sir.
Okay, okay, okay. See, if there is no doubts, simply I go to stop the share screen, please. Just wait. Yeah. So come to any clarifications here? Any clarifications here? Anything else? Any clarifications or please anything?
No, sir.
Where is your CRs here? What about the CRs? Nikhil is there or not? Saurish. Okay, okay. See that attendance here. What about the attendance? I will take care of that morning attendance. Okay. Yeah, because almost now 60, 61 is there. Okay, I think morning also same. Say out of 60, 71. Okay, I'm going to retain the same one. Okay. Yes. I say I already uploaded that video on the